Okie dokie. So today's date is March 31st, 2020, which I cannot believe. And as I said earlier, we're going to start talking about gases. So we're going to talk about the different measurements of pressure. We're going to talk about different gas laws, and we're going to learn how to do some math associated with it. So yes, it's math, but it's not as involved as Chapter 7. So hopefully it'll give you a little bit of reprieve. So gases are really important. If you breathe, then you care about gases, okay? You're breathing air, which contains oxygen. You're breathing out carbon dioxide, two very important gases. So understanding how to do calculations about gases, understanding the pressure, volume, temperature, things of that nature, and how they adjust when you adjust the conditions that the gas is in, really important. We're going to start by talking about the properties of gases. We're going to cover the kinetic molecular theory, and we're going to talk about some measurements and the units that you're going to need to get familiar with for this chapter. The kinetic molecular theory talks about gases and the small particles that comprise gases and what these particles do, how they interact, how quickly they move, what type of movement they have. So the first part of the kinetic molecular theory states that a gas consists of small particles that move randomly with high velocities. So if you think about a gas like a container filled with gas, think about the gas particles like a room full of toddlers, okay? They move randomly, they run everywhere, they bump into each other. That's a gas. They have very small attractive force between them. So that means that when they bump into each other, they just kind of bounce away. There's no interactions. They don't stick together. Gases just kind of hit each other, bounce off of each other, and keep moving. They don't want to really interact. A gas consists of small particles that occupy a much larger volume than the volume of the molecules alone. So if you were to take the molecules in a gas, let's say in this cylinder on the right-hand side, if you were to squish all of those down to where you just had the volume of those little balls that represent the gas particles, it would be a very tiny volume in comparison to the very large container that the gas is in. Gas particles, like toddlers, are in constant motion and they move rapidly in straight lines. Maybe the toddlers don't move in straight lines, but constant motion, fast, random motion. We use the Kelvin temperature to talk about the average kinetic energy of molecules. So when you talk about a temperature in Kelvin, you're talking about the average energy of the gas particles in a container. So understanding these 5 different points about the kinetic molecular theory will help you understand how gases move, how they interact with each other, and their stops. Any questions there? So it's pretty much just you'll have some questions to help you understand the kinetic molecular theory in your mastering chemistry homework. So there are 4 different properties that we're going to talk about with gases: pressure, volume, temperature, and the amount. So pressure, so you see this table here, there's the definition of each of these. So pressure, we're talking about you have gas in a container. That gas is exerting force on the walls of the container. That force is called the pressure. The volume is the container of the gas. Temperature, we just talked about temperature with the kinetic molecular theory, and the average kinetic energy of the particles in a container, that's the temperature in Kelvin. The amount is the quantity of gas that's present in a container. And most of the time, we're going to be talking about grams and moles. So moles will be N. So I will remind you of that as we go through and we start doing calculations, that where does N come from? That means moles. So the volume of a gas, it's the same as the container. So if I have a container, a poorly drawn container like this, if I take the gas particles and put it into a bigger container, and let's say that this is my volume 1 and this is my volume 2, the volume of the gas is going to change based on the container. It's usually measured in liters or milliliters, and it increases in temperature at constant pressure, which that's getting us to the gas law. So if we have the volume, it will increase when the temperature increases and pressure is constant or unchanged. So that's a different way to write out what was written in this bullet point here, this last bullet point. So I will use like P or V or T with the arrows for up or down to increase or decrease as my shorthand. So that's the volume of a gas. The temperature of a gas we already touched on. It's the measure of the average kinetic energy that the gas molecules have, and it's measured in Kelvin. Remember that you can take degrees Celsius and convert it to Kelvin by adding 273. And with Kelvin, there's no degree sign. So please don't put one. That's wrong. When the temperature of your gas decreases, that means that you have less kinetic energy. So that means you have fewer collisions. So let's say that it was almost nap time and those toddlers are getting a little tired. They're not going to lay down unless you make them, but they're probably moving a little bit slower. They're not bumping into each other as much, perhaps not causing as much mayhem as they normally would. When you increase the temperature, you have more kinetic energy. When you do that, you increase the number of collisions that you have. You take those toddlers after nap time and you give them sugar. Then you should probably leave the room because they're going to be running all over the place within 15 minutes. Increase in collisions, spills, and mayhem. Okay? So increase in temperature means more kinetic energy, and you're going to have more collisions with your gas. Pressure talks about the force that the gas exerts on the walls of the container. There are a lot of different units that you can use for measuring pressure. You will often see millimeters of mercury, abbreviated mmHg, atmospheres. You'll see torr. Pascals and pounds per square inch, those are, especially pounds per square inch, that's more of a imperial system kind of thing. You'll see that maybe with power tools and things like that that use air. You're not going to see that as much in the world of chemistry. The gas particles that exert pressure on us from the atmosphere, that's called atmospheric pressure. And so we experience 1 atmosphere of pressure. One way that we can measure the atmospheric pressure is using a barometer. And that pretty much takes into account the atmosphere, so the gases in the atmosphere, pushing down on liquid mercury and causing that mercury to go up into this inverted tube. The level of mercury in the tube is literally measured in millimeters. So that's where the millimeters of mercury come in. So 1 atmosphere is the same thing as 760 millimeters of mercury, and that is also the same thing as 760 torr. And the torr is just a unit to honor the person who invented the barometer, which is Evangelista Torricelli. So they said, hey, I know we have these millimeter of mercury, but let's just throw out another unit. We'll honor this person, give them a little something to pat them on the back. So when you see torr and millimeters of mercury, or Hg, it's the same thing. This is a summary of all the different units for pressure, the abbreviations, and the unit equivalent to 1 atmosphere. So if you have 1 atmosphere, then you have 760 millimeters of mercury, or 760 torr. You can also use inches of mercury, pounds per square inch. So all of these are here. For our purposes, a lot of what we're going to do is going to be with atmospheres, millimeters of mercury, and torr. But with this chart, you'll be able to convert back and forth between all of these. So talking about atmospheric pressure a little bit more, if you're standing outside or wherever you are, sitting down in your home, you're feeling atmospheric pressure. Now, you don't really feel it consciously, but it's there, okay? As you go higher up, let's say that you decide to retreat to the mountains because coronavirus was just getting to be too much and you just wanted to be alone. As you increase your altitude, your atmospheric pressure that you experience decreases. The inverse is true if you were to say, you know what, the top of the earth, great. You know what's better? Underneath. I'm going to go maybe find a place that's below sea level, hang out there for a while. That means that you're decreasing your altitude and your atmospheric pressure is going to increase, okay? So whichever one makes sense to you, let that stick in your brain. For me, it makes sense to think about going up into the mountains, your atmospheric pressure drops. The atmospheric pressure is affected by all kinds of things, including the weather, and we already talked about altitude. So on a hot day, you might actually be experiencing a little bit more atmospheric pressure than on a rainy, cloudy day. It's not necessarily enough to feel, although some people claim that they get headaches and things, or they have sinus issues on rainy days or very cloudy days because the atmospheric pressure changes. I don't know, I'm not them, but I usually don't feel that. So let's do some math. We talked about a lot of stuff. The main thing is to understand volume and temperature, pressure, understand what those different variables are, and the kinetic molecular theory that describes how gases behave. Now we're going to do a conversion. So there are all these different types of units for pressure. We need to be able to convert from one unit to another. This is a review of just doing conversions and using conversion factors. So if this is something that you struggle with, please, please, please let me know, and we can set something up for office hours or outside of office hours. So here we have a gas that's exerting 0.280 atmospheres of pressure on its container. We're supposed to express the pressure exerted by the gas in millimeters of mercury. As always, I rewrite the question. So I have 0.280 atmospheres, and the question is, how many millimeters of mercury is that? Now, you will need to use that chart that tells you the unit equivalents of one atmosphere in all those different units. Now, I've been doing this for a long time, so I already know off the top of my head that one atmosphere is equal to 760 millimeters of mercury. So we need to take this equation and write a conversion factor. If we're trying to go from atmospheres to millimeters of mercury, we have to have a factor that has what we want to get at the end on the top and what we already have at the bottom. So what are we going to put at the top of our factor? You can write it in the chat box. Yep, we're going to put the millimeters of mercury. So that's 760 millimeters of mercury. That leaves the one atmosphere on the bottom. That's what we already have information about atmospheres. And if you're wondering, like, okay, where did those numbers come from? Remember, we just wrote an equation that says one atmosphere is equal to 760 millimeters of mercury. So that's where that came from. And then the one atmosphere. So hopefully that illustrates it a little bit better for you. So now all we have to do is the math. We take this factor and we multiply by 0.280 atmospheres. Atmospheres cancel. Try putting that into your calculator and tell me what you get. Yep. So your calculator is going to say something like 212.8. But we need to have 3 sig figs here because our answer or our initial information has 3 sig figs. So we're going to report it as 213 millimeters of mercury. That's how simple it is. You go to that chart, you figure out one atmosphere or whatever it is that you're equating is equal to whatever. You make your conversion factor and do your multiplication. Questions on that? If you're good, you can raise your hand. Okay. All right. So we've got people saying they're good, so we're going to move on. Yeah, I can go back to that chart. Give me 1 second. Let me try to navigate to it. Here we go. There's the slide. Let me know when you took a picture of it. I'll also just give you that information for whatever one you need, but okay. You're welcome. Let's see if I can get back to where we were. Okay. All right. So for whatever reason, now the internet doesn't like the X symbol. That's okay. All right. So we've got a learning check. I want you guys to try number 1. What is 475 millimeters of mercury expressed in atmospheres? And remember that 1 atmosphere is equal to 760 millimeters of mercury. This is the reverse of what we just did. Take a minute, and then I'll check back with you. Maybe I should do elevator music so you don't think I left you. I don't have any good music to play for you. I don't want YouTube to come for me, so it'll just have to be quiet. It looks like we already got an answer. As you get your answers, you can add your answer to the fold. Anybody else get an answer? Yep. All right, we were just working on number 1, but Jordan, it looks like you did number 2 as well. That's fine. So yeah, number 1 is B. And for those of you who didn't get it, what you should do for this problem is take your 475 millimeters of mercury and you're multiplying by the conversion factor that has 1 atmosphere at the top, 760 millimeters of mercury at the bottom. And what you're actually doing is dividing 475 by 760. And you should get 0.625 atmospheres. Don't forget to put your units. And then for number 2, Jordan, you already did it, but it is also B. For this one, you would take your 2 atmospheres and multiply by your factor that has 760 millimeters of mercury in the top and 1 atmosphere at the bottom. And that would give you 1,520 millimeters of mercury. So if you have problems with that, don't be shy. Let me know. If you don't want to say it now, you can wait till the end of class, or you can send me an email, come to office hours. All those things are available to you. So now we're going to do some more conceptual Learning check questions. The downward pressure on the mercury in a barometer is greater than, less than, or the same as the pressure of the atmosphere. You can put your choice, A, B, or C, in the chat. Greater than, less than, or the same as. We have a guess for A. Just take a guess. A, B, or C. You have a vote for B. Okay. The answer is actually C. So when you think about a barometer, there's the atmospheric pressure pushing down. And that pushing down pushes the mercury up. So the downward pressure in a barometer is the same as the pressure of the atmosphere. Question 2 asks about a water barometer. So a water barometer is 13.6 times taller than a mercury barometer. And I'll tell you that the reason is A. Water is much less dense than mercury. The density of water is about 1 gram per milliliter. So it needs to be a lot taller to be able to do the same thing as the mercury. Are there questions about that? So when you go back over your notes, make sure that you understand these 2 questions about barometers. So we talked about the different properties of gas: pressure, volume, temperature, amount. And now we're going to talk about, there are 3 gas laws that we're going to talk about today. The first one is Boyles Law. Boyles Law, we're looking at pressure and volume. In a nutshell, if you increase the pressure, you decrease the volume. If you decrease the pressure of a gas, you increase the volume. So pressure and volume are inversely proportional. What you do to one, the opposite happens to the other. This is all when the temperature is constant. So no change in temperature or the amount of gas, okay, your N. So if you hold those 2 the same and you decrease the volume of a gas, you're going to increase the pressure because now you have less space. So that same amount of gas particles is bouncing around in a much smaller space. So let's do a little bit of a learning check to think this through. Let's say that we have this initial cylinder here, okay? And where this cylinder is indicates the volume. So if this cylinder moves down, the gray part with the handle, if that moves down, then that means it is a decrease in volume. And if it moves up, it's an increase in volume. Let's say we took this initial cylinder and we decrease the pressure. Will the volume increase or decrease? What happens to the volume? We decrease the pressure, so the opposite happens to the volume. That's right, it's going to increase. So cylinder B is going to represent that because we have an increase in volume. The cylinder went up. Conversely, if you increase the pressure, you're going to decrease your volume, and that's represented by cylinder A. So remember, again, increase pressure, decrease volume. Decrease pressure, increase volume. So that's Boyle's Law. When you think about breathing, we can also think about Boyle's Law. So when you inhale, your lungs get bigger. That means you're increasing the volume, which means that the pressure in your lungs decreases. And the air that you're inhaling flows to the lower pressure in the lungs. When you exhale, your lung volume decreases. You're pushing that air out. So you're going to decrease your V, which means that the pressure in your lungs increases. And the air flows from the higher pressure in the lungs to the outside. So you're exhaling the carbon dioxide and all the other things that your body didn't take in. So that's a practical way to think about Boyle's Law and how it affects you every day. Now let's do a calculation. One of another way that we can represent Boyle's Law is like this. P1V1 equals P2V2. P1 and V1 are your initial conditions, and the P2V2 are your final or your new conditions. And we can use this to figure out the new volume or new pressure of a gas if we change one of these two variables. So let's say we have a refrigeration system that uses Freon, which this stuff, they're trying to outlaw it. It's really bad for the environment. If we have an 8-liter sample of Freon gas that's initially at 550 millimeters of mercury, and then we change its pressure to 2,200 millimeters of mercury and keep temperature and moles the same, what is the new volume? So let's rewrite that. That's a lot of information. Whenever you have these gas law problems, it's best to write out what you know first, then you can figure out which gas law makes sense to use. So we have a volume of 8 liters. That's what we're starting with. We also have a pressure that we'll call V1 at 550 millimeters of mercury. Now this says the pressure has been changed. So that implies that we're looking at our new or our final pressure, and that's going to be 2,200 millimeters of mercury. And the question is asking, what is our V2? The first thing that I do is figure out what the heck it is that I'm solving for and what are the units. Our first volume was given to us in liters, so that means that when we solve this, our volume, our new volume, is going to be in liters as well. We have this equation, P1 V1 is equal to P2 V2. We need to solve for V2. So I like to circle the variable that I need to solve for. Now I divide to isolate V2 from everything else. So I divide by P2 on both sides. And with some rearranging, what I get is V2 is equal to, get rid of the P2 on that side, P1 over P2 times V1. Now the reason why I broke it out that way is because the pressure will cancel out so that you're left with liters or whatever your volume is. So it's easier to see that. So then we plug in our numbers. For P1, it's 550 millimeters of mercury. Our new pressure, the P2, is 2,200 millimeters of mercury. And we're multiplying that by our initial volume of 8 liters. Try putting that into your calculator and see what you get for the new volume. Yep. So your answer should be 2 liters. And don't forget that we need to report it with 2.0 because we need 2 sig figs. When you write out your pressure over pressure like this, it's very easy to see that you cancel out the millimeters of mercury and the unit you're left with is liters. Now we can also reason through this problem to check our answer, make sure that it makes sense. So we're starting with 8 liters. We don't know what our new volume is going to be, but we can predict whether or not it should increase or decrease based on what the pressure does. If we're going from 550 millimeters of mercury to 2,200 millimeters of mercury, so P1 to P2, that is a pretty big increase. So that's an increase in pressure. That means that our volume has to decrease. When we look at our V1, it's 8. Our V2 is 2 liters. So yes, it decreased. So we should always make sure that your logic and your math add up. If they don't agree, then you need to revisit the problem. Questions about that? We're going to do some more, but if you need me to go through this again, raise your hand. Okay. Anybody else? I can run it through again real quick. So we're starting with 550 milliliters or millimeters of mercury. I'll switch over to a pointer here. And that pressure goes with 8 liters. That's the volume of our initial system. When we increase the pressure to 2,200 millimeters of mercury, the question is, what will our new volume be? We have an equation that says the pressure and volume for one system, if you change something in that system, you can calculate the new pressure or the new volume. So P1V1 is equal to P2V2. You isolate V2 by dividing both sides by P2. Then you solve. You put in all of your numbers that you wrote out from the problem. And you're taking the ratio of the two different pressures and multiplying by the volume. Since we're going from a lower pressure to a higher pressure, that means that we have an increase in pressure, which means that our volume should decrease. When you do the math, that's what you see. Your new volume is 2 liters when our initial volume was 8. So if you still need more help with that, we're going to do some more problems. So here's another problem to try. We have a sample of helium gas, and it has a volume of 120 milliliters and a pressure of 850 millimeters of mercury. What you have to do is find the new volume if the pressure is changed to 425 millimeters of mercury at a constant temperature and no change to the amount of gas. So before we start doing the math, the first question is, we're going from 850 millimeters of mercury to 425 millimeters of mercury. Are we increasing the pressure or decreasing the pressure of the helium gas? You put it in the chat box. We're going from 850 millimeters of mercury to 425 millimeters of mercury. Is that an increase or a decrease in pressure? It's a decrease. We're decreasing the pressure. So what does that mean for our volume? If we're decreasing the pressure, our volume, is that going to go up or down? It's going to go up. It's going to increase. So that means that whatever new volume we get, it should be more than the initial volume that we were given in the problem. So now let's set it up. Always write out the different variables that you have. So our initial conditions, we have a volume of 120 milliliters and a pressure of 850 millimeters of mercury. Our new conditions, we have the pressure changing to 425 millimeters of mercury. And we don't know what our new volume is, but we know that whatever number we get is going to be milliliters. Doesn't matter if it's liters or milliliters, doesn't matter what units the pressure is in, as long as P1 and V1 have the same units as P2 and V2. Now we set up our problem. We're solving for V2, so I'll circle that. That means we have to divide by P2 on both sides to isolate V2. When you do that, you get that V2 is equal to P1 over P2 times V1. What I want you to do is try plugging in the numbers from the initial conditions and everything else and see what you get for the new volume. So I'll give you a minute to try that. That's exactly what I got. 240. When you fill it in, you should have 850 millimeters of mercury on the top. You're dividing by 425 millimeters of mercury. You're multiplying that by 120 milliliters. Notice that your pressure units cancel. You're left with milliliters. You do the math, you get 240 milliliters. How many people were able to get that? Raise your hand. Okay. You can lower your hand now. Thank you. If you did not get that, speak now, forever hold your peace. You come to office hours, all the things, okay? One more learning check, and then we're going to move on to another law. So we have helium gas in a balloon, has a volume of 6.4 liters, and the pressure is 0.7 atmospheres. At 1.40 atmospheres, which one of the balloons, A, B, or C, represents the new volume? So the question is, volume. Will it increase or will it decrease when you go from a pressure of 0.7 atmospheres to 1.4 atmospheres? You can put which letter represents the balloon that represents the increase or decrease that happens when you change the pressure. A, B, or C? If we're going from 0.7 atmospheres to 1.4 atmospheres, we're increasing the pressure. If we're increasing the pressure, what has to happen to the volume? Right. It has to decrease. So that means if we were doing this, it would be A. That would represent the new volume. So be able to do the math and be able to do the reasoning. The next law is Charles's law, and that relates temperature and volume of a gas while holding the pressure and the amount of gas constant. So if you have two cylinders, or we have one cylinder and you increase the volume, then the temperature is going to also, let's write this down. So let's say we have a cylinder like this, and then we increase the volume. When we increase the volume, we also increase the temperature. Temperature and volume are directly related. So increase your temperature, increase your volume. This is an example of how you can rearrange Charles's law. So this is Charles's law. V1 over T1 equals V2 over T2. If you want to solve, then you have to cross multiply. And I'll show you what that really looks like. So let's say that we wanted to solve Charles's law for T2, which is right here. The first thing you do is cross multiply. So you get V1 times T2 is equal to V2 times T1. Then I circle the variable that I want to isolate. In this case, we're solving for T2. So I'm going to divide both sides by V1. And when I do that, I get T2 is equal to V2 over V1 times T1. So it's very similar to the math that you have to do for pressures. You just have to first do the cross multiplication. I guess to name our second step, we have to isolate the variable. So does that make sense on how to solve Charles's law for a variable? Raise your hand if you're good with doing this kind of math. Okay. Or you can say yes. Yeah. Good. All right, so we're going to move on. So if you're good with it, we're going to move on and do some problems. Okay. So that other one in there was to solve for V2. If you feel like you need some more practice, you can do that, and then you can email me or come to office hours if you have questions. But I want to get to doing problems, and we still have one more gas law to finish. So here we have a balloon with a volume at a certain temperature. The volume is 785 milliliters at 21 degrees Celsius. The temperature drops to 0 degrees. What is the new volume, assuming that constant pressure in moles? Okay. Remember, with gas laws, you have to have Kelvin. So if you see degrees Celsius, you must convert. The very first thing that I do is I write out my variables. What do I have? And what am I solving for? We have our initial conditions where the volume is 785 milliliters at 21 degrees Celsius. We have to convert that to Kelvin. So we do 21 plus 273, and that will give us Kelvin. It's 294. V2, we don't know, but when we solve it, it will be in milliliters. T2 is 0 degrees Celsius, which is 273 Kelvin. Always make sure that your temperatures are in Kelvin, or else you will not get the right answer. Now we take our gas law and when you're doing these problems, you're going to need to be able to identify which law you need to use. So Charles's law relates volume and temperature. Since all we have are volumes and temperatures, we have to use Charles's law. You're not going to be told, use Charles's law to figure out. You're going to need to be able to figure out yourself. So I wrote down Charles's law. I'm going to do the cross multiplication. Then I'm going to circle which variable I want to solve for. In this case, it's V2. I'm going to divide both sides by T1. And then I get V2 is equal to T2 over T1 times V1. Take the information that we have for V1, T1, and T2, plug it in, and see what you get. I'll start writing it out here. Yep. So with 6 figs, it's 729 milliliters. Now I want to vote, because I have more problems that we can do, or we can move through this and get to the third gas law. So raise your hand if you want to move to the third gas law. Okay. Any other votes for moving forward? All right, so we've got a few people who are ready to move on. All right. So here's what we'll do. I will quickly set up this problem and not solve it, and then we'll move on to the next gas law, just so people can see it set up again. So it'll be kind of the best of both worlds. Hopefully everybody will be happy. So in this one, we have a sample of oxygen gas. We have a volume and a temperature, 420 milliliters, temperature of 18 degrees Celsius. So that's going to be our V1 and T1. Remember, convert to Kelvin. At what temperature will the volume of the oxygen be 640 milliliters? That means we have a V2 of 640 milliliters, and we don't know what our T2 is, but they want us to report it in degrees Celsius. So when we do the math, your initial answer will be in Kelvin. So make sure you convert. Okay. If you have issues doing that, you can absolutely let me know. But I'll let you know the answer is B. If you don't get B, you should be concerned and let me know. All right? The last gas law that we're going to go over today is Gay-Lussac's law, and that equates pressure and temperature. You'll notice that P1 over T1 equals P2 over T2 looks a heck of a lot like the Charles law that we just did. So that means pressure and temperature are directly related. When you increase the pressure, you increase the temperature, and vice versa. That's, of course, assuming that the volume of gas and the amount of gas are remaining constant. So we're only looking at two variables, keeping all the others the same. When we're solving for a variable, it's very similar to what we just did. So let's say we want to solve for P2. First thing you have to do, again, is cross multiply. When you cross multiply, you get P1 T2 is equal to P2 times T1. Then identify which variable you're trying to isolate. In this case, we're doing P2. That means you're going to divide by T1. And when you rewrite this equation, you get P2 is equal to T2 over T1 times P1. So it's very similar math to Charles's law. Let's do a sample question. I want you guys to set up the whole question. So you have gas, the pressure is 2 atmospheres, and the temperature is 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius with constant volume in moles? So don't forget, change those Celsius to Kelvin and figure out what the new pressure is. I will slowly start setting up the problem, and I want to see what you guys get. When you have an answer, go ahead and put it in the chat box. And Jayla wins the prize, which I don't have any prizes, but you get the prize of knowledge, increased knowledge. So I'll finish setting up the problem here. So it's the same thing that we just solved for with the example of how to solve for P2. And when you plug everything in, it should look like this. Your T2 is 335 Kelvin. Your T1 is 291 Kelvin. You're multiplying that by P1, which is 2 atmospheres. When you do all that, you cancel out your Kelvin, you're left with atmospheres, and your calculator is going to say something like 2.302 with a bunch of other numbers after it. But we only want 2 sig figs. So we're going to say 2.3 atmospheres. So it's very similar to Charles's law, except it's pressure and temperature. But for the sake of time, we're going to go through and talk about vapor pressure really quickly. But this is another problem that you can try on your own, and I'll give you the answer to this one. The answer is 239 degrees Celsius is your T2. So if you go back and watch this, you have the answer, and you can try to work it out yourself. If you don't get that answer, you can let me know. So the last bit that we're going to talk about is vapor pressure and boiling point. When we talked about atmospheric pressure, we said that it changes. And so if you're at a really high altitude, you're going to experience less atmospheric pressure than someone that's below sea level. When you think about boiling something like boiling water, what's really happening is the molecules in that water, let's say, has enough energy to break away from the surface of that liquid and become a vapor. That takes a good amount of energy. Eventually, everything will evaporate. If you close a container, you're not necessarily heating or anything, you just have a container with some liquid in it, eventually you're going to get vapor accumulating on the lid. The pressure from that vapor is called vapor pressure. When you're at your vapor pressure, and that's equal to the external pressure that's pushing down, that's when you're boiling, okay? So your liquid exerts its own vapor pressure at a given temperature. So temperature changes the vapor pressure, okay? When you're boiling a liquid, the vapor pressure that's present is equal to the external pressure. So if you're at a really high altitude, your external pressure is going to be lower than if you were at sea level. So a lower external pressure means that you're going to have a lower temperature for boiling. It's also called the boiling point. So this table tells you the pressure and the boiling point of water. So you can see as you go from 70 degrees Celsius to 180 degrees Celsius that your pressure increases. So lower atmospheric pressure, you're going to experience a lower boiling point. So you should be able to, this is a depiction of some of the ways that vapor pressure are used. So you can do this in a lab, like on the left, or on the right. Autoclaves are used in research all the time and in hospitals. And so they reduce the external pressure so that, or they increase the external pressure, so that you can get a higher temperature for steam to sterilize things. So those are just two examples. When you think about boiling points at different atmospheric pressures, you should be able to answer this learning check question about why water boils at a lower temperature in the mountains than at sea level. So I want you to think about that, be able to answer it. If you can't, then we can revisit that for the next class. But I don't want to go over. It's 4:45. So you'll have an assignment. It's going to focus on using the different gas laws and converting pressures from one unit to another. So that will be posted on Blackboard shortly, and it will be due tomorrow by midnight. So if it's 11:59, your homework needs to be submitted. If it's 12:02, that's late, okay? So submit that homework on time, and if you have questions, you can come to office hours tomorrow from 11 to 1. With that, if you have any questions, you can ask me now. You can email me. Otherwise, you're free to go.